So now we're asked to consider yet another scenario that instead of the two sticking together, we're back to them bouncing off each other. And that situation we mentioned might be that where x is slower than y, and x is slower than y. Then we had this scenario where x is catching up to y, and this had 5 and this was 2, and now they bounce off, and this one has a speed of 2 and this one has a speed of 5, or this direction is 2. Just in terms of the possibilities, we do need x to be slower. So now they want to know what is true of the momentum of the system. What we know is the momentum of the system is always conserved. There are no exceptions of the momentum being conserved, but they gave us the speeds afterward. And you can see from the numbers, since the masses are equal to each other, we had a 4, and since the masses are equal to each other, then we know the magnitudes of the momentum must be the same afterward. But we could do the calculation out to see. We have the momentum of x plus the momentum of y, and the momentum of x prime plus the momentum of y prime. So momentum of x was 2 times 4, and I believe they did tell us the masses to the same mass. They didn't tell us what the mass was, but it's the same. So I'm just going to put in 2. The momentum of y, the velocity was 5, excuse me. And then we have this 2, and the other velocity was minus 2. No, it's positive 2. And then afterward, we know the mass of x is 2, and the velocity is also 2, and y, which has a mass of 2, has a velocity of 5. And so you can see that these quantities, that must be true, that the momentum is conserved. But that the fact that momentum will always be conserved, except maybe in an experimental context where something bizarre happens, we should always expect, because it is the universal law for the universe, that momentum of a system is conserved if the system is defined properly. And since the system is x and y and there's no other bodies bringing about the change, then the momentum should be constant. Now, it should also be the case because of the false dichotomy we spoke about, where we have EK, EK0, EK to EK0, and we have the case where it is all conserved. So this is 1.0 and 0.0. And we said that neither of those cases is happening. However, this is, in a real life, that's the case. It should not be, there are no extremes. The extremes don't exist. But in this case, they're giving us the values of the before and after. And so now we can actually compute the change in kinetic energy. And so we have the kinetic energy of x plus the kinetic energy of y minus the kinetic energy of x prime plus the kinetic energy of y prime. And so we have 1/2 of 2 times 5 squared plus 1/2 of 2 times 2 squared minus, and afterward you'll notice the same thing happens. 1/2 of 2 times 2 squared plus 1/2 of 2 times 5 squared, and that those two sums will be equal to each other so that the kinetic energy also remains constant. Now, in a theoretical setting, there will always be some that's lost, but in this case, they gave us the velocities, and we then determined that it is constant.